In this video, I'm going to anger anyone and everyone that knows anything about radio. Additionally, for those who knows how to build stuff in general, viewer discretion is advised. But more specifically, I want to build everything I need to receive pictures of the Earth from a satellite, like it's 1994. Which means I'd like to only use information, tools and materials that would have been available to a happy amateur in '94. When reading about the World Wide Web, I saw that there's a website that could show you recent pictures of the Earth, and I wonder if I could do that too. With some digging, it seems the answer might be yes. Since the 60s, the National Oceanic and Atmospheric Administration of the USA, or NOAA, has had these satellites up in the sky that constantly beams down what they see in real time. It's sent on a VHF band with frequency modulation, and the actual data signal is a fairly low bandwidth audio signal. After scouring BBSs and pestering radio amateurs, I think I figured out what I need, so let's just run through it. Since I want to receive and decode the picture on my computer, I need a computer. The computer then needs to run software. To my computer I need to connect a radio of some sort. And for the radio I need an antenna. Right, so let's start with the software. There were a number of programs that could be used to decode these pictures. One of the popular alternatives at the time was JVFax, which can encode and decode a lot of slow-scan TV-like formats, including the APT encoding used by the NOAA satellites. This does just what I need, so I guess that's settled? Another one of the ones I found was Channel X, but this one requires the entire satellite pass to be recorded first. This takes like 20 megabytes of disk space per satellite pass. If you have watched this channel before, you know that I don't have 20 megs disk space to spare. I currently got about 2 megabytes. So the choice is obviously JVFax, but I'll get back to this later. Something that this version of JVFax requires is a hardware digitizer interface. It can't use the sound card. This will take the audio signal from the radio and digitize it. The schematics for this interface is included with the program. It's quite complicated, but building it should be fairly straightforward. So I decided to build it. But I'm not making a PCB for this. Instead, I'll just wire wrap it. Wire wrap is an old technique for building prototypes in low volume production. It's been around since the 60s, but it started falling out of fashion during the 90s, with surface mount components, ever higher clock speeds and cheaper breadboards. Nowadays it's practically extinct. It looks a bit iffy to the untrained eye, but a wire wrap connection was usually more reliable than a soldered connection. Heck, even the Chernobyl power plant computers were built with wire wrapped backplanes. If the foundation is a perforated board like this, it may or may not have solder pads. I picked a board with solder pads, so that I could selectively get better access to power and ground if I think I need it. If there's no solder pads, you just glue the sockets to the board. The sockets have these extra long square posts. I'm using a basic hand tool, but there were electric wire wrap guns and automated machines too. With this I use 30 gauge wire. You strip off an inch of insulation each end, and then load it into the tool. It has a separate hole with a slot that the wire goes into. Then you just place the tool over the post and twist. There's a notable change in resistance when it's done wrapping the wire. And there it is, a wire wrapped. When you make a mistake, you just use the other end of the tool and twist it the other way. Hopefully without damaging any other wire wraps on the post. I found that the most common mistake for me is when I forget that the pins are mirrored. As you wrap everything from the bottom side, the pins get flipped to how I'm used to seeing a chip. The long square posts are important, so you can't easily include passive components. Wire wrap is best suited for digital designs. I use these dip plugs with solder lugs as a platform for passives, that I then plug into a socket. These were great in some ways, but I did have a few problems with bad soldering that wasn't immediately obvious. I used them extensively on the first of the two boards I made. On the second board, however, I ran out of space. And there isn't really all that much more to it. Just a whole bunch of wires to wrap. There is a calibration routine in JVFax to use when you build the thing, but I wasn't able to get it working. It seems something is off in my build, and it's taking an inverted signal. So I ended up just looking at the signals in a scope and going on vibes. I also gave the boards a house. The D-sub isn't straight, but at least it's the right gender. I may have messed that bit up earlier. The two boards are wired to the connectors and LED with a ribbon cable. To simplify the wire wrapping, I use these dip-style IDC crimp plugs. With the software sorted, it's time to look at the radio. The NOAA polar orbiting satellites transmit on 137-ish MHz, and a bandwidth of about 50 kHz is recommended to deal with Doppler shift. This isn't much fancier than a regular FM radio, except it's 20 MHz higher up in frequency. The same thing to do would be to buy or borrow a suitable scanner. So I decided to build my own. I talked to someone that knows something about radio, and they handed me an application note for the Motorola MC3562 chip. It looked detailed enough to be dangerous. The chip has been around since the late 80s, and it seemed to do what I needed it to. To tune it to a specific frequency, I also need a PLL, preferably a computer programmable one. So I went looking in the 1994 Alpha catalog, and I found me a PLL. The diamond thing means they have a datasheet. Based on this, I think I can puzzle together a radio. The application note is very specific about you not breadboarding or wire wrapping this thing, as you can't do that with radio stuff. Makes sense, as wire wrap and breadboards are notoriously terrible for high frequency signals. So I guess I'll need to make my own PCB. I could do it by just drawing on a piece of copper clad, or I could do it on a computer. Another way back in the day was to use a transfer film. On that, you'd rub on ready-to-use symbols and use curve tape to make traces. This would then be transferred to a photosensitive film and made into an original for making PCBs. I think this is a bit too complicated to just freehand, so I'll make it on my computer. And there's two parts to making a PCB on a computer. First, I need to make a schematic. From the schematic, I can get a Netlist, which is a list of connections to make. This feeds into a PCB layout program. For the Schematic Capture, I found a freeware DOS program called EEDraw. It can generate netlists too, so it should be up to the task. In order to make my schematic, I need to have all the symbols. Most of them are already in the library that comes with EEDraw, but there's a few I have to make myself. The libraries use a fairly simple text-based format, so I was able to figure out how that works. There is no graphical editor for this. Beyond that, I basically just needed to study the application note and make a schematic along those lines. The program itself is a little clunky. The library viewer and place component functions are not connected, so you need to remember the name of the symbol you want to place. Other than that, it went pretty smoothly. By the end of it, I had grown a bit of a fondness for these full-screen crosshairs. It definitely felt CAD-like. My main gripe is that it feels cumbersome to edit things after you've placed it, to the point that it's easy to just delete the thing and insert it again. I couldn't get printing working though. Any attempt to export a picture out of this thing was completely garbled. The PostScript output was almost acceptable. But with the schematic sorted out, it's time to make the PCB. There wasn't really any free options for making PCBs on MS-DOS or Windows that I could find, but on a Zika shareware CD-ROM, I found a demo version of Protel for Windows 1.0. I think it'll do just fine for this PCB. This is a program that you want a high screen resolution for, so I'm bumping it up to 800 by 600 for this segment. With that sorted, I'm now in Protel. One of the limitations of this demo version is that you can't edit the library. Most of my components are already in the library, but some aren't. This is a problem, but not an unsolvable one. And no, I'm not getting the full version. I'm sure that would cost money. Instead, I got this hex editor of the same Zika shareware CD. Opening up the library file, its structure looks pretty approachable. It starts with this table of components. It has a field for name, length of symbol, and a position in the file for the symbol. The length of a symbol seems to be measured in draw commands, and the position is in paragraphs. Paragraph is an old term for a 16-byte chunk, which was a convenient size to work with in real mode DOS due to how real mode segments work on x86. So just add an extra 0 to the end of the position and you get the position in bytes. Makes sense since this entire library format seems to be built on 16-byte chunks. The symbol itself consists of these draw commands. The one starting with 05 draws straight lines. The 03 draws a pad and has a second 16-byte block for the pad name, with the first byte being the length. 01 draws a circle. All coordinates are 16-bit signed integers and are measured in thou. One limitation of this hex editor is that I can't expand the file. Not a big problem though. I don't need these huge LGA footprints. So I'll just clear this one out as not used in the components table, and now I can use its space for my own purposes. I started out by just copying an existing component and modified that, but by the end of it I was able to write them from scratch. There was a lot of converting between decimal and hex, as well as from millimeters to thou, but that was pretty much the only tedious part of it. Aside from that, it wasn't much worse than making schematic symbols for EEDraw. Now comes the next problem. I need to load my netlist from EEDraw into Protel. The format doesn't seem to be compatible though. Looking at my netlist, and the netlist that came with one of the example PCBs, it's easy to see that they are different. But a more important difference is that my netlist doesn't have a list of components. The Netlist having a different syntax could have been solved easily with a small program, but the missing component table would need to be added manually. So I decided to just open these up side by side and manually convert the Netlist to the right format. When I write the component table, I also need to select a component in Protel's library to map it to. With the components listed and mapped to a physical footprint, I can continue with the Netlist. This again wasn't so bad. Each net starts with a name, followed by all the pins it connects to. This is also an opportunity to clean up the netlist that EEDRAW produced. While EEDRAW had power symbols for VCC and ground, it doesn't combine the nets when you have created multiple of these symbols. After spending a few hours reading from one notepad and writing to the other, I had my netlist and I was ready to import into Protel. Which brings us to the main event, actually laying out the board. For a reason I'll mention when I'm done, I've already done a bit of practice for this off camera and already have a good idea of where I want to place and route everything. So I start out with my intended outline. As far as I can tell, there is no dedicated edge cut layer. You just put down a track on the keep out layer. I'm using large VS for mounting holes. And now I'll load the netlist I prepared earlier. This creates a huge pile of components and draws a rat's nest of connections to make. I'm starting up by just moving and rotating all the components to where I want them. It's easy to end up with clunky workflows, so it takes a bit of practice. It's definitely the kind of program where you want to make heavy use of keyboard shortcuts, which is unfortunate since they don't seem to work on my computer. When I practiced in a VM, they worked without problems. Just to rotate a component without keyboard shortcuts, you have to select the component, then go into the menu to select rotate, type in the angle. Rotations are done counterclockwise. Moving components are best done by clicking on an empty space and typing in the reference designator. Otherwise, you might not always grab the component by pin 1, which can screw up the alignment. Another fun quirk is when you double click on a component. You shouldn't move your cursor until the dialog comes up. It doesn't look at where the cursor was when you double clicked. It looked at where it is when it's done thinking. Another thing you might have noticed is that the graphics looks all garbled and corrupted. It doesn't redraw the screen unless you tell it to, and the partial redraws it does aren't exactly perfect. There's a reason why they put the redraw button right on the toolbar. About an hour later, I had all the components placed. I'll be printing the pattern out on my 9-pin dot matrix printer, so I'm using a 30 thou track width to cope with the low resolution. 30 thou is about 0.75mm. So, time to start connecting everything. Because I'm lazy and I don't want to align anything if I don't have to, this will be a single layer board. And let's just say that if you've used modern software, the way Protel 1.0 handles nets is a bit clunky. First, I tell it to optimize the nets. This tries to shuffle the connections around so that they are made as close together as possible. And to start laying out a track, I've found that you can't really use the track option. You go into Auto and select Manual Routes, and off you go. It's worth mentioning that it doesn't enforce DRC rules. It doesn't stop you from routing over existing tracks of other nets. Unlike in a modern PCB editor, you can't just connect the track to the nearest thing of the right nets. If it tells you that this connection goes to the other side of the board, then that's where it wants you to connect it. Something I'm not doing here that you really should do with radio stuff is a copper field for ground planes. As far as I can tell, copper fields are just utterly broken in this version of Protel. Every attempt to use it has just ruined the board. So I'll skip it and hope for the best. And not even an hour later, I'm done. So at this point, I start printing out all the patterns, which is copper, silkscreen, and drill guides. First as PostScript, and then on my 9-pin dot matrix printer. I need to get as much data as possible out of the software at this point, because another limitation of this demo version is that you can't save. That's why I practiced beforehand. I had to do all of this in one go. With a copper pattern printed onto paper, I'm ready for the next step. And the next step is to transfer it to an overhead transparency. Just looking at my printout, it isn't great. It isn't very dark and there's gaps in its coverage. I could touch it up with a marker, but I think I'll just let the photocopier deal with it. Maximum darkness, maximum contrast, minimum sharpness. No toner saving. Maximum toner density, please. And it's looking a lot better. I then copy this over to a transparency with the same settings, and I think I'm good to go. If you were doing prototype PCBs back in the day, you'd probably have the following equipment. You start with a copper-clad board with photoresist on it. You put it in the UV exposure box with a mask you made in between for a few minutes. You then put the board in a tub with a weak lye solution, known as a developer. Photoresist that was exposed to light will come up with some gentle rubbing. You then prepare a solution of sodium persulfate and fill up your etching tank with it. Let it preheat the water to about 50 degrees Celsius. It also has an air pump, which helps speed up the etching. Then you just put the PCB in the tank for a while and let it etch away all the copper that isn't protected. Then take it out and rinse it off. The remaining photoresist comes off with acetone. So, it's time for me to make my PCB. And this video is sponsored by a friend who could be bothered to dig out his equipment out of a closet. I'm not doing sponsorships. So, step 1 is to prepare the etching solution. It'll take a while to heat up, so it makes sense to start with this. Used etching solution keeps well, so we'll start by just adding whatever's already sitting around. The blue color comes from copper sulfate, from previous board etchings. It wasn't quite enough, so we needed to make some more. We're using sodium persulfate, which keeps well. If it's been sitting around for a while, it might get a bit lumpy, but it should still be fine. With that added to the etching tank, we can turn on the heater. And don't forget the bubbles. If you don't have a heated tank, you could just carefully microwave the solution, I guess. With the tank up to temperature, we can prepare the developer. This is done by dissolving a teaspoon of caustic soda in a liter of water. The gloves and goggles are not for show, for this step it's absolutely required. With the solution prepared, it's time to preheat the UV exposure box. It takes a couple minutes for the UV tubes to get up to power, and it can mess up your exposure times if they aren't up to temperature. These are UVA, so they aren't super dangerous to be around, but we chose not to stand there and stare into them while they were heating up. Next, we can place the film on the glass surface with the toner side up. Next, the protective film over the photoresist on the copper clad was removed and it was placed against the transparency. And then we turned it on for 3.5 minutes. After this, the exposed photoresist can be washed off with some gentle rubbing in the developer solution. With that done, it's time to etch. There isn't really any strict timing to this step. You'll leave it in there until it's done. Etching doesn't happen evenly in this tank, so we have to move it around a bit. If you leave the board in for too long, some of the protected copper can start to degrade. If you don't have a tank like this, a small tub on a countertop works too. About 20 minutes later, it was starting to look done, so we took it out and rinsed it off. Finally, the remaining photoresist can be rubbed off with some acetone. Last step is to drill all the holes. It's a bit fiddly to do, as most of the holes are 0.9mm. But in the end, we decided the drill press was the best option. It took a good 40 minutes, but in the end we got a PCB with most of the holes where they should be. With a bare PCB in hand, it was time to assemble it. Like usual, you start with the low profile stuff, like resistors and diodes. From there, work your way up with taller components. After struggling for a bit with the solder pins, I did a quick power up test to make sure that there aren't any shorts before I soldered in the chips. With that confirmed, I put the chips and the rest of the components in. Everything's a bit crooked and wonky, just like the electronics of my childhood. With a somewhat decent soldering job, as well as a bodge resistor that makes the PLL work, I was ready for the software side. But before I do that, how does this let me tune the radio? I'll be glossing over a lot of details here, but this is the gist of it. The PLL takes two inputs, a resulting clock and a reference clock. Both the resulting clock and the reference clock is divided with a programmable amount first. That result is then compared. If the resulting clock is slower than the reference clock, it increases the output voltage. And if the resulting clock is faster than the reference clock, it decreases the output voltage. This output voltage goes to the voltage control oscillator in the radio chip. More voltage means faster clock. So the PLL just tries to make the two clocks equal. And the divider steps lets us manipulate the resulting clock. This radio chip contains two components called a mixer. A mixer takes two input radio frequencies and spits out a whole bunch of combinations. The first one combines the input signal from the antenna with the frequency generated from the voltage control oscillator. The latter is the local oscillator for this step. The most important output from the mixer is the input RF shifted down by the local oscillator. So if you got a signal at 110 MHz and your local oscillator is at 100 MHz, the signal gets shifted down to 10 MHz. But due to how this works, there is also a mirror around your local oscillator. So 90 MHz also gets shifted to 10 MHz. Effectively tuning into two stations at once. You're supposed to have an input filter that removes the signal at your other mirror. I don't know how to build one of those, so I'm crossing my fingers and hoping for the best. This then gets output into a bandpass filter, which will at 10.7 MHz pass but filter out others. This then goes into the next mixer, which has a fixed local oscillator of 10.245 MHz. This will shift the signal down to 455 kHz, after which it goes into a second filter before finally arriving at the FM detector. So, I need to set my PLL and therefore my local oscillator to 10.7 MHz above or below the frequency of the station I want to tune into. Now I just need to make a small utility to program it from my computer. I'll be connecting it to my printer port, and the PLL is basically talking SPI. And I'll be bit banging it over the data pins. To actually calculate the dividers, I took the easy way out. I use a fixed divider for the reference clock, and calculate the corresponding input divider. You could get better precision by calculating the optimal divider for both, but maybe some other time. Now that I have a radio, I need an antenna. Hidden in the documentation for that other program, Channel X, was a description for how to build an antenna. There's only a minor problem with the instructions. I'm not super into radio terminology, but these instructions appears to be written entirely in gibberish. It's either that or that they are in Finnish. I went over the instructions with a highlighter and marked all the words that looked real. I think I can work with this. But before building it, let's just quickly go into what's so special about this antenna. If all I wanted was VHF, I'm sure an old TV antenna would do just fine. But radio waves, just like light, can be polarized. Here on Earth, we tend to use linear polarization, which means radio waves can either wiggle horizontally or vertically, or technically somewhere in between if your antenna isn't straight. This is why the antenna on your FM radio hinges, by the way. Polarization can vary depending on country and radio station. Something like a TV antenna would be built for linear polarization. When you got satellites hurling across the sky, this isn't as convenient. Most satellites that aren't geostationary tend to spin a little in relation to an observer on the ground. If the polarization was linear, then you'd constantly have to turn your antenna to compensate. So these kinds of satellites instead use circular polarization, which isn't as sensitive to the transmitter spinning around its antenna axis. These come in two flavors, right-hand and left-hand polarization. If you point the way the signal goes with your thumb, your other fingers will point the direction to feel the spinning. NOAA's VHF signals are right-hand circular polarized. Having the right type of antenna will get you a better signal, sometimes by a little, sometimes by a lot. But enough physics, let's get to the build. First, I need 4 lengths of aluminium tubing, 50 centimeters each. And a hole drilled into each for a ring cable lug. I got some help with that. This then needs to go into a holder of some kind. So I found this cork sanding block in a closet that I drilled some holes into. Next, I need a 35 centimeter length of coax, which will act as a delay line. The idea is that you have 2 antenna elements 90 degrees apart, and you also want to connect them together electrically 90 degrees apart. So 35 centimeters of coax is about a quarter of the wavelength when going through copper. I'm using regular European TV coax for this. I put some ring cable lugs on my delay line, as well as the cable that will go to my radio. As I can't access the tube from more than one side with this cork block, I glued some nuts to the inside of the antenna elements. I really should have tapped the holes, but oh well. I screwed on the terminals following the instructions, I think. The feed cable shield went to A, because I started with A, and the shield was the easiest one to move. To make a holder for this, I used some rubber glue I found in a drawer, and glued the cork block to a cardboard tube. The cable out from it is about 8 meters long, allowing me to have the antenna outside, and my computer inside on the upper floor. It should be as short as possible, but And this should now be an antenna. This means I should be able to test this thing now. But there's a few more things I need to do. First, I need to figure out my coordinates. Before the time of widespread GPS, it wasn't exactly common knowledge to know what coordinates you're on. So how would you figure that out? Aside from asking someone that knows, which is likely anyone with a boat, we also used to have this thing called a map. I don't need a super accurate number, but a ballpark one is helpful. And in this book of maps, I can see that I'm at 18 degrees east and 59 to 59.5 degrees north. On a different page in the same book, we can also see a picture of Sweden captured on an earlier satellite, NOAA 7. Now that I know where I am, I can move on to a bit of software that I found on a Simtel MS-DOS shareware CD-ROM. The thing about these satellites is that they only fly past a couple times a day. While there are several satellites in orbit, they each transmit on a different frequency. So you kinda need to know when and where to listen to capture one of these things. And step 1 is to set up my location. If you live near one of these presets, you don't need to know your coordinates, I guess. I also need to tell it what things in orbit that I'm interested in. But with this information, I can do a scan for satellite passes. And since these satellites capture visible light, I'd like a midday pass if possible. This NOAA 13 pass with an 88-degree elevation looks good, so I'll write that down. Now it would be helpful to know roughly where in the sky it will pass, to better plan my antenna placements. So I enter another mode of this program, tell it the time of day I found earlier, and let it step through a minute at a time, and I can get a visualization of its trajectory. But that's it! I now have all the information I need. Now, since NOAA 13 is no longer in service, I'll instead be listening to NOAA 19. So I'll start by configuring my radio for that. NOAA 19 transmits on 137.1 MHz, so I'll start by configuring my radio for that. I also need to load the Visa graphics extensions, and then I can start JVFAX. I configure it to receive NOAA APT, and then we wait. Sadly, I never got any pictures. The satellite just couldn't quite make it through the noise floor. I think we're gonna need a bigger signal. Looking for inspiration in one of my electronics project books, I find a VHF antenna amplifier design. It's based on a single dual gate transistor and a few passives, so it doesn't look too horrible to build. And for this one, I'll use yet another construction technique. I'll build it Manhattan style, which at least was pretty popular in ham radio circles. I start off with a blank piece of copper clad. I then cut out a bunch of these little squares of the same material. I then glue these onto the board to create islands. The baseboard is my ground plane, with no interruptions. The islands is where the other signals go. This design also uses these weird coils that are tapped off one turn into them. And I guess this just shows how normal intuition falls apart when you're dealing with RF. The antenna input and ground go to the same coil, separated by just one turn. And somehow this doesn't kill the signal, which is very weak. This thing is supposed to amplify everything by 20 dB, and looking at it with a modern SDR dongle, it looks like it does. So hopefully this is all I need. The reception is better, but I'm still not able to actually decode anything in JVFAX. And this is pretty disappointing. As an attempt of last resort, I tried playing back a pass I recorded using the same antenna and preamp, but using a modern SDR dongle. And with this, it's able to actually detect an incoming image. And it is decoding something. Sadly, the result is still pretty underwhelming. But I think the main limitation is this Digitizer box. I must have done something wrong when building it, but the huge mess of wires is more than I'm able to untangle. If I decode a recording made with my antenna, preamp and radio with modern software, it's obvious that I'm receiving something. Like, you can tell this is Europe. And this image, which is hard to see because it was past the twilight, is definitely a valid signal. And the antenna and preamp is working great. Using these and an SDR dongle, I was able to capture this picture, which, when colorized, isn't too far off the nice picture we saw earlier in my book. But in the end, I guess this was just another over-ambitious project that ended up in disappointment. So if you used JVFAX back in the day to receive pictures from these satellites, how did that work out for you? Let me know in the comments, I'm curious. And before I end the video, here's a last bit of trivia for you. In this video, I've been tuning into NOAA 19, and you may have seen pictures of this satellite before. During the build of it, there was a bit of an oops moment. $130 million it cost to repair it. Launched in 2009, this is also the last of the bunch to be equipped with this old analog APT transmitter. APT over VHF has been around since the 60s, so it's had a 60-year run now. And there's currently only NOAA 19 and NOAA 15 left, and once these go dark, then that'll be the end of APT. I originally intended for this video to go up a few weeks before the satellites are shut down, but I just heard they got shut down this week, while the expected end of life was in September. So unfortunately, I can't tell you to go out and try it yourself now. But I think that'll do for this video. Check back next week when I'll be having a look at Motif 1.2 for Linux. Until then, thank you for watching.